morning students. This is lecture 2 under module 5 and as you know that we are discussing biomass physico chemical and thermochemical conversion in this module, and today's class is an important one in which we will be discussing about two most important thermochemical conversion processes. One is gasification and another is pyrolysis. So, let us begin. So, gasification is a partial oxidation process that converts biomass into carbon monoxide and hydrogen with less amount of carbon dioxide and water. Now, this process occurs at higher temperatures above 700 degree centigrade without combustion with a controlled amount of oxygen and or steam. Gasification typically uses only 25 to 40% of the theoretical oxidant. It can be either pure oxygen or air to generate enough heat to gasify the remaining unoxidized fuel, producing syngas or producer gas, which are used as fuels. Gasification generates lower amounts of some pollutants such as SOx and NOx in comparison to combustion. Now, basically combustion is a full oxidation process in which all the biomass is completely oxidized, okay, whereas in gasification we use less than theoretical oxygen that is required, okay, for the partial oxidation process. So, biomass gasification processes are generally designed to produce low or medium energy fuel gases for the manufacture of chemicals or hydrogen. For more than 1 million small scale air blown gasifiers for wood and biomass derived charcoal feedstocks were built during World War II to manufacture low energy gas to power vehicles and to generate steam and electric power. A significant number of biomass gasification plants have been built, but many have been closed down and dismantled to or mothballed. The pyrolytic gasification of biomass has been interpreted to involve the decomposition of carbohydrates by depolymerization and dehydration followed by steam carbon or steam carbon fragmentation reactions. So, pyrolytic gasification is a type of gasification process. I would like to say during this discussion is that pyrolysis is a, though it is a separate thermochemical conversion process, but whenever gasification is actually happening. So, the second step is the pyrolysis reaction. So, before the gasification reaction really begins, so pyrolysis happens. Okay. We will discuss in our subsequent this one discussion today when we will talk about the reaction mechanisms, then it will be little more clear. So, some of the coal gasification processes are also suitable for biomass feedstocks. Since the conditions required for coal gasification are more severe than those needed for biomass, some coal gasifiers can be operated on biomass or biomass coal feedstock blends. Indeed, some gasifiers that were originally designed for coal gasification are currently in commercial use with biomass feedstock, because coal has been depleting day by day. The chemistries of coal and biomass gasification are quite similar in terms of the steam carbon chemistry and are essentially identical after a certain point is reached in the gasification process. Note however, that biomass is much more reactive than most of the coals. Biomass contains more volatile matter than coal, and the pyrolytic charge from biomass are more reactive than pyrolytic coal charge. The thermodynamic equilibrium concentrations of specific gases in the mixture depend on the abundance of carbon, hydrogen and oxygen, the temperature as well as the pressure. Biomass is gasified at lower temperatures than coal, because its main constituents, the high oxygen cellulose and hemicellulose, have higher reactivity than oxygen deficient carbonaceous materials in the coal. In addition of co-reactants to the biomass system such as oxygen and steam, that can result in large changes in reaction rates, product gas compositions and yields, and selectivity as in coal conversion. Biomass feedstocks contain a high proportion of volatile materials, 70 to 90% for wood compared to 30 to 45% for typical coals. A relatively large fraction of most biomass feedstocks can be devolatilized rapidly at low to moderate temperatures, and the organic volatiles can be rapidly converted to gaseous products. The charge formed on pyrolytic gasification of most biomass feedstocks have high reactivity and they gasify very rapidly. For biomass and waste biomass, steam gasification generally starts at a temperature near to 300 to 375 degrees centigrade, again depending upon the type of feedstock. Undesirable emissions and byproducts from the thermal gasification of biomass can include particulates, alkali and heavy metals, oil, starch and some aqueous condensates. It is important to avoid gas turbine blade corrosion and corrosion by removing undesirable particulates that may be present. The removal of tars and condensable gases may also be necessary. Furthermore, utilization of the sensible heat in the product gas improves the overall thermal operating efficiencies. Non-turbine applications of the gas may also be able to take advantages of the process that provide clean pressurized hot gas such as certain downstream chemical synthesis and fuel uses. So, what happens basically when the gasification is happening in a gasifier, any type of gasifier, we will also discuss in our class today what are the different types of gasifiers available, and of course, pyrolysis reactors or pyrolyzers. So, there are many obnoxious byproducts that actually getting formed, including some of the tar also, right. So, this needs to be removed frequently, otherwise it will create a problem with the inside the reactor. Okay. So, the reactor vessel will get corrode if there are some corroding elements present, and if you do not take it out for a prolonged time and they keep on presenting, then there cannot be a proper reaction will proceed basically. Okay. So, research on thermal biomass gasification in North America has tended to concentrate on medium energy gas production, scale up of advanced process concepts that have been evaluated at the PDU scale, and the problems that need to be solved to permit large scale thermal biomass gasifiers to be operated in a reliable fashion for power production, especially for advanced power cycles. So, PDU means the power distribution unit. So, this is a typical scheme. Please have a look. The first one here it talks about the gasification routes, the second one is about the gasification reactions. We will discuss that in detail in our next slide. So, let us understand, this is what I was telling you, that pyrolysis is a part of the entire gasification process. Okay. If you stop here and do only pyrolysis, then it becomes a pyrolysis reaction, okay, and then subsequent products. But then if you go on for the next step, then it is that step is basically the gasification process. Let us understand. So, biomass needs to be dried, okay. For any thermochemical conversion process, we have discussed last class in even one of the pre-treatment classes, we have discussed that biomass needs to be dried to a particular moisture level, otherwise the reaction may not proceed in a proper direction. So, it is dried, then it goes for pyrolysis, right. So, after pyrolysis there may be so many different types of things. You can see that gases, liquids, oxygenated compounds, and solid is basically the char. So, if you go for a gas phase reactions like cracking, reforming, combustion, water gas shift reactions, so you get carbon monoxide, hydrogen, methane, water, carbon dioxide, and some other smaller components. If you go for the char gasification reactions, so you get carbon monoxide, hydrogen, methane, water, carbon dioxide, residual carbon. So, the if you talk about the product from the gasification is mostly the synthesis gas, okay, or maybe producer gas. So, these are the some of the reactions that happens actually, the carbonation reaction, oxidation reaction, water gas shift reaction. Water gas shift reaction takes place at very high temperature, right. Then methanation and steam reforming. So, this is given in detail. We will see in the next slide the reactions. Okay. So, 4 to 5 different types of reactions happen. The first one is the dehydration or the drying process, as I have shown you here, okay, the drying process, right. So, that occurs at around 100 degree centigrade. So, the resulted steam is then mixed into the gaseous flow and may be involved with subsequent chemical reactions, predominantly the water gas reaction if the temperature, high temperature actually exists, right. Okay. So, after that the biomass or the whatever the vapor that is getting generated, actually that goes to the pyrolysis stage, which is called as devolatilization state. So, that occurs between 200 to 300 degrees, sometimes up to 350 also. This process releases the volatiles, thereby producing char as an effect, almost 70% weight loss. So, char is getting produced because there is severe weight loss, almost approximately up to 70%. The process is however dependent on the properties of the biomass, which eventually determines the structure and composition of the char. Then in the next step, it goes the combustion reaction. So, the char then undergoes the combustion reactions to primarily form carbon dioxide and small amounts of carbon monoxide, okay, that provides heat for the subsequent gasification reactions. So, you can see that here the fuel, okay, let us understand it is a dried fuel or after the drying fuel, then when it is when the devolatilization or the pyrolysis reaction is proceeding, we get char, right, and some of the tars and hydrogen, some methane, some gases. Okay. You can trap it or you can leave it depending upon how much you are producing. Then this char subsequently goes for the combustion reaction and gasification reactions. Okay. So, the gasification process occurs at the char reacts with steam and carbon dioxide to produce carbon monoxide and hydrogen. Now, there is a reversible gas phase water shift reaction, which we talked in the step 1 also, and this happens at very high temperatures. Okay, and this reaction, water gas shift reaction, reaches equilibrium very fast when the temperature is very high, thereby balancing the concentrations of carbon monoxide, steam, carbon dioxide and hydrogen. The major product of syngas or synthesis gas is of course carbon monoxide and hydrogen, and if certain amount of carbon comes into contact with a proper amount of oxygen and get combusted, then it will result in some amount of carbon dioxide. Okay. So, let us understand the different types of gasification process variations. So, the primary products of biomass pyrolysis under conventional pyrolysis conditions are gas, oil, char and water. As the reaction temperature increases, gas yield increases. That means what predominantly it means, when you stop during pyrolysis, at the pyrolysis reaction, that the entire thermochemical conversion process becomes pyrolysis process. Then you will get gas, oil, char and water. Okay. That is what we get from the pyrolysis reaction, but when we are proceeding in a gasifier and doing the gaseous gasification reactions, okay, so then we will get the gases, there will be more gaseous product yield. So, it is important to note that pyrolysis may involve green or pre-dried biomass, and that product water is formed in both cases. Water is released as the biomass dries in the gasifier and is also a product of a chemical reaction that occur even with bone dry biomass. Even if the dry biomass is almost close to 95-98% or close to 99% dry. So, unless it is rapidly removed from the reactor, this water would be expected to participate in the process along with any added feed water or steam. One of the more innovative pyrolytic gasification process is an indirectly heated fluidized bed system. We will discuss about that later. Now, this system uses a 2 fluid bed reactors containing sand as a heat transfer medium. Now, sand holds the heat for a long time and it is a good medium for doing the heat transfer. So, that is why it is being used and it is low cost, readily available, can be recycled back. So, combustion of char formed in the pyrolysis reactor takes place with air within the combustion reactor. The heat released supplies the energy of pyrolysis of the combustible fraction in the pyrolysis reactor. Heat transfer is then accomplished by flow of hot sand from the combustion reactor at 950 degrees centigrade to the pyrolysis reactor at 800 degrees centigrade, and then the sand can be returned back or recycled back to the combustion reactor. So, this configuration separates the combustion and pyrolysis reactions. That means, predominantly instead of a single gasifier under which drying, pyrolysis, gasification, combustion, everything is happening, you have 2 different reactors, in which in one reactor pyrolysis is happening and another reactor combustion is happening. Okay. And it yields a pyrolysis gas that can be upgraded to a high energy gas, okay, which is a substitute of natural gas, is called SNG, by shifting, scrubbing and methanation with regard to nitrogen separation. So, there are certain, the shifting, scrubbing, methanation are the polishing steps. So, let us have a look at this particular 2 bed fluidized reactor system which is being used to produce methane. Okay. So, you can see this is the fluidized bed combustion process, this is the fluidized bed pyrolysis process. Both are using the sand is getting as a heating medium and the sand is getting interchanged or recycled between these 2 beds, right. So, when the air is supplied to combustion reactor, whatever you get is the combustible products, right. Then this one under the pyrolysis reaction, the shredded feed organics are being actually fed your feedstock. Okay. So, and whatever you get is basically the gas and char. Now, under there is a separator, the separator actually separates the char and the gas phase. So, the gas phase means the pyrolysis gas phase. Okay. Then it goes to the some shifting reactions, carbon monoxide, scrubbing to remove carbon dioxide, then methanation reaction to get methane, pure methane. And you have to purify it, and part of the pyrolysis gas is being recycled to maintain the reaction conditions inside the pyrolysis reactor, and the char is getting fed to the combustion reactor, where it is go undergoing the gasification reaction. So, the pyrolysis gas with hybrid poplar feedstocks typically contains about 38% carbon monoxide, 15% carbon dioxide, 15% methane, 26 mole percent of hydrogen and 6% of C2S. Now, this is a medium energy gas having a higher heating value of about 19.4 megajoule per meter cube. The projected gas yields are about 670 meter cube of pyrolysis gas or about 200 meter cube of methane per dry ton of feed if SNG is produced. Okay, substitute natural gas. It is a very nice process. Okay. So, many thermal conversion processes can be classified as partial oxidation processes in which the biomass is supplied with less than the stoichiometric amount of oxygen needed for complete combustion. When the oxygen is supplied by air, low energy gases are formed that contain higher concentrations of hydrogen, carbon monoxide and carbon dioxide than medium energy gases. When we use pure oxygen or oxygen enriched air or even air also, gases with higher energy values can be obtained. In some or certain partial oxidation processes, the various chemical reactions may occur simultaneously in the same reactor zone. Most of the time you will understand that the gasification process is being done in a single gasifier. In a single reactor, let us call it single reactor, all sorts of reactions are happening, there are different zones. Okay. But when you what we have discussed in just before this particular last slide about the two fluidized bed systems, that is essentially done to produce when you look for two different things. One is this syngas, producer gas, whatever it is, and one is the pure methane. Okay. So, that was particularly aimed to produce methane as well as the usual syngas. So, then you go for a two bed systems. Otherwise, if you are only product you are looking for is a syngas, whether high quality energy carrier or low energy carrier gas, whatever it is, depending upon the feedstock and other process conditions, a single gasifier is more than enough. So, in others the reactor may be divided into zones, that is what I was just telling. Okay. A combustion zone that supplies the heat to promote the pyrolysis in a second zone and perhaps a third zone for drying, the overall result of which is partial oxidation. So, this is another example of the partial oxidation process. So, here the production of synthesis gas in a 3 zone shaft reactor furnace. Okay. Please understand that it is a 3 zone shaft reactor, but it is a single reactor. Now, let us understand. Okay. So, the 3 zones. So, here you feed the biomass. Okay. So, when the biomass is being fed, okay, this is the zone which is responsible for the first reaction, that is the drying zone. Okay. Then comes the second zone, that is the pyrolysis zone. Okay. Then it comes to the third zone where oxygen or air enriched with oxygen is being fed to do the combustion process in a, of course, less than theoretical demand. So, whatever you get is basically the molten slag, then it goes to feed quenching and the gas will be recovered here on the top of the reactor. Then it goes to water scrubbing and you get a downstream part of that or the bottom product is being separated and recycled. So, this is the fine liquid that is getting recycled, the wastewater is again treated and then discharged, and whatever is coming here is the almost pure gas after the water scrubbing. Then it goes to electrostatic precipitation to remove fly ash and other certain components. Then you cool it and you get product gas, and whatever the when during the cooling process certain amount of moisture, whatever it is actually still remains in the gas phase will condense, and then that can be fed back to the separation unit. Okay. So, in this process coarsely shredded feed is fed to the top of the furnace. As it descends to the first zone, the charge is dried by the ascending hot gases which are partially cleaned by the feed. So, please try to understand what is happening here. You feed it. Okay. So, when you feed initially here drying is happening. So, the drying is happening, then pyrolysis combustion. When the pyrolysis and combustion reaction is happening at the bottom portion, the gas is moving upward. So, this gas is also doing the drying process. Correct. Do you understand this? Okay. So, that means in a single thing you do not have to supply extra energy, okay, or heat to take care of the drying process. The product gas whatever is producing, that is doing the drying. So, the gas is reduced in the temperature from about 315 degree centigrade to the range of 40 to 200 degree centigrade. The dried feed then enters the pyrolytic zone, in which temperature ranges from 315 to 1000 degree centigrade, again depending on what feed you are using. For different feedstocks, the temperature may vary. So, the resulting char and ash then descend to the hearth zone, where the char is partially oxidized with pure oxygen. The hearth is the bottom zone basically. Slagging temperatures near 1650 degree centigrade occur in this zone, and the resulting molten slag of metal oxide forms a liquid pool at the bottom of the hearth. Continuous withdrawal of the pool and quenching forms a sterile granular frit. The product gas is processed to remove fly ash and liquids, which are recycled to the reactor. A typical gas analysis is almost 40 mole percent of carbon monoxide, 23 mole percent of carbon dioxide, 5 mole percent of methane, 2% of C2S and 20 mole percent of hydrogen. This gas has higher heating value of about 14.5 megajoule per meter cube. An example of the gasification of biomass by partial oxidation, in which air is supplied without zone separation in the gasifier, is the molten salt process. In this process, shredded biomass and air are continuously introduced beneath the surface of a sodium carbonate containing melt, which is maintained at about 1000 degree centigrade. As the resulting gas passes through the melt, the acid gases are absorbed by the alkaline media, and the ash is also retained in the melt. The melt is continuously withdrawn for processing to remove the ash and is then returned to the gasifier. No tars or liquid products are formed in this process. Thus, with about 20, 50 and 75% of the theoretical air needed for complete oxidation, the respective higher heating values of the gas are about 9, 4.3, 2.2 megajoules per meter cube. Basically, biomass gasifiers can be categorized into several reactor design groups. A descending bed of biomass, often referred to as a moving or fixed bed with counter current gas flow updraft, and a descending bed of biomass with counter current gas flow, that is called downdraft. A descending bed of biomass with cross flow of gas, a fluidized bed of biomass with rising gas, an entrant flow circulating bed of biomass, and a tumbling beds. There are various types of arrangements can be possible. So, some of the designs that are being tested and are commercialized are fixed bed, moving bed, suspended bed, fluid bed reactors, entrant feed solid reactors, stationary vertical shaft reactors, inclined rotating kilns, horizontal shaft kilns, high temperature electrically heated reactors with gas blanketed walls, single and multi hearth reactors, ablative, ultra fast and flash pyrolysis reactors, and several other designs. You can see that there are so many different types of designs and reactors of the reactors that is already being tested. There are clearly numerous reactor designs and configurations for biomass gasification, probably more than in the case of coal gasification systems, because of the relative ease of thermal biomass conversion. So, let us now understand the different biomass gasification design. We will just try to understand in a glance how this looks like. Okay. So, briefly a fixed this you can see in this particular diagram. I have shown two different type of fixed bed gasifiers. One is the updraft gasifier, another is the downdraft gasifier. Now, a fixed bed gasifier can be either updraft, that means what is happening in the updraft, the fuel is getting dropped from the top, gasifying agent from the bottom, okay, and the downdraft. So, both fuel and gasification agent occurs from the top, it is a co-current flow. Okay. Here the flow is counter current. In updraft gasification, the char at the bottom of the bed meets the gasifying agent first, and complete combustion occurs, producing hydrogen and carbon dioxide and raising the temperature to almost 1000 degree centigrade. So, the hot gases percolate upwards through the bed, driving endothermic reactions with unreacted char to form hydrogen and carbon monoxide, with consequent cooling to 750 degree centigrade. The gases pyrolyze the dry biomass, which is descending, and also of course, at the near the top of the reactor, and also dry the incoming biomass. Updraft gasifiers typically produce between 10 to 28% tar in the produced gas, which is far too high for many advanced applications. It is not a good thing, of course. The allowable tar levels depend on the downstream application. These are around 0.05 grams normal per meter cube, okay. 0.005 gram normal per meter cube, 0.001 gram normal per meter cube for gas engines, gas turbines and fuel cells applications respectively. in contrast to an updraft gasifier, in a downdraft gasifier, which is the closed loop, the gas flows concurrently with the fuel. A throttled gasifier has a restriction part way down the gasifier, where air or oxygen is added and where the temperature rises to 1200 degree to 1400 degree centigrade, and the fuel feedstock is either burned or pyrolyzes. The combustion gases then pass down over the hot char at the bottom of the bed, where they are reduced to hydrogen and carbon monoxide. The high temperature within the throat ensures that the tar formed during pyrolysis are significantly cracked, that is the homogeneous cracking, with further cracking occurring as the gas meets the hot char on the way out of the bed, heterogeneous cracking, leading to a less tarry of gas. Some disadvantages of a throttled gasifier are: the constriction at the throat affects the type of biomass that can be successfully gasified. A low moisture content is required, almost 25 weight%. Ash and dust are significantly present in the exhaust. Tar can still be up to 5 gram normal per meter cube, needing further cleanup. Biomass gasifier design. So, it is this is a bubbling fluidized bed system. Okay. So, the biomass is fed from the side. Okay. You can see this is the main bubbling fluidized bed. Okay. Here the biomass is being fed using a hopper and a feeding screw. There is a screw system which is slowly actually feed in a particular rate. Okay. And there are grids here. This is the fluidized bed. Then whatever the gasification product is going basis the gas phase, okay, that needs to be separated from the fly ash and other components. Okay. So, that will be done using a cyclone separator. Then you get the hot product gas, and whatever it is remain the solid fractions will again come down to the bottom of the reactor. So, either they will be burnt again or they can be collected from the bottom. So, the biomass is feed from the side and are below the bottom of the bed, and the gasifying agent's velocity is controlled, so that it is just greater than the minimum fluidization velocity of the bed material. The product gas exists from the top of the gasifier, and ash is either removed from the bottom or from the product gas using a cyclone. So, next design is a circulating fluidized bed. So, circulating fluidized bed known as CFB systems use two different integrated units. In the first unit, there are two systems you can see, this is one column, there is another column here. Okay. So, the first unit is called the riser, okay. The second unit is called the downcomer. Now, in the first unit, which is known as the riser, the bed material is kept fluidized. So, this is the main reactor where the fluidization is happening by the gasifying agent. So, you see that we feed the biofuel feed, or the feedstock is being fed here somewhere, okay, and from the bottom you collect the ash, right, and then when the gas goes out and there is a downcomer here, here you basically do some processing, some other things are also there, okay. You collect the product gas here, so there is air preheater, and then part of that gas is also being recycled back. So, in the riser, the biomass is fluidized by the gasifying agent with a higher velocity that then found in the bubbling fluidized bed, the BFB, which we discussed. Now, this allows the bed material to be fluidized to a greater extent than the BFB, and the overall residence time is higher due to the circulation, which is effected by passing the product gas and entrant bed material through a cyclone, which separates the product gas from the bed material, which is recirculated back to the riser. So, we will now discuss about a special gasification technique, which is called supercritical water gasification. Water above its critical point, which is 374.12 degree centigrade and a 221.2 bar, is termed as supercritical. Now, under these settings, the liquid and gas phase do not exist. There is it is a phase between a liquid and gas phase, it is called supercritical phase, and in that phase particularly the water shows distinctive reactivity and solvency characteristics. So, the water in supercritical phase will have both the properties of a gas phase as well as a liquid phase. Solubilities of organic materials and gases which are normally insoluble are enhanced with a decrease in solubility for inorganics. So, supercritical water gasification has been applied to wet biomass without the need for pre-drying. So, this technology is been actually developed to take care of the wet biomasses. Please understand that when the biomasses are highly wet or has high moisture content, then you need a significant amount of energy to basically dry them before you feed them to a gasifier or a pyrolyzer. So, if you go for a supercritical water gasification system, then whatever the water or moisture is present inside the biomass will actually behave like a reactant. Okay. So, this is the major advantage and this is the aim of developing the supercritical water gasification system. So, product gas from this SCWG mainly comprises hydrogen, carbon dioxide, methane and carbon monoxide. The carbon monoxide yield is comparatively low as carbon monoxide transforms into carbon dioxide through the water gas shaft reaction. So, this is the unit. Okay. So, this supercritical water gasification, the main reactor is of course very costly. You can think about the high temperature and high pressure it is required to make the water into the supercritical stage, right. So, here the main reaction is happening, then whatever you are getting here the product, it goes through some heat exchanger and there is a phase separator, you get clean water and you get the product gas. Okay. And whatever portion from this is a combustion air and methane is recycled and being collected as a flue gas or may be used for other purposes. So, by employing the supercritical water gasification process, even liquid biomass such as olive meal water can be utilized with the production of low tar hydrogen gas. It is a very nice technology, the only problem is the cost and special types of reactors of course, and that is why it leads to the extra or additional cost. Tar and coke formation are curtailed by rapid dissolution of product gas components in supercritical water. Wet biomass treatment without pre-drying, liquid biomass treatment such as olive meal wastewater, high hydrogen yield, high gasification efficiency and low tar formation are the main advantages of this particular technology. So, if you we are just further discussing about that particular technology only. If you look at this particular slide, you can see that hydrogen, this is the blue one is the hydrogen production. You can see that it enhances exponentially after this 600 degree centigrade. So, up to 600 degree centigrade it is almost in a saturated stages the production is happening. The moment we cross 600 degree centigrade, there is a exponential increase in the hydrogen gas production, while the carbon monoxide, the carbon monoxide is the red one, it decreases after 600 degree centigrade. It is almost after 660 or 650 you can say that. So, methane decreases to 540 degree centigrade and then remains almost constant when even the temperature is increased. Major limitations include requirements of high pressure, high temperature resistance and rust resistant materials, consequently increasing the investment cost and high energy requirements. The major motivation behind biomass gasification is to exploit a large variety of waste materials as feedstock, to increase resource efficiency and to reduce adverse climate change via carbon dioxide mitigation. Although gasification is a key technology to utilize biomass waste, it poses many potential kinds of risks which have a significant impact on society and the environment at large. One of the main problems is the potential emissions of particulates. Some dioxins, PAH, carbon monoxide, SOx, NOx and some volatile organics. These pollutants can interact with humans through inhalation, ingestion and dermal contact and thus pose a grave threat to human health. Ash and tars are noteworthy elements which have potential for environmental contamination, should be properly disposed of. So, gasification is a system which has an inherent risk for fire and explosion vulnerability, especially since the gasifiers operate at high temperature and pressure. This probability enhances significantly when hydrogen is the desired product. It is highly flammable and therefore necessitates a great amount of caution. The waste streams formed require a suitable disposal system to be implemented that meets all the legislative guidelines, especially this environmental guidelines. Techniques like low temperature circulating fluidized bed, which can produce ash with negligible pH impurity, pose little threat to the environment, meaning that this ash can also be used as a fertilizer or soil enhancer basically. So, next is we will discuss about pyrolysis. So, biomass pyrolysis can be described as the direct thermal decomposition of the organic components in biomass in the absence of oxygen to yield an array of useful products, liquid or solid derivatives and fuel gases. Eventually, pyrolysis processes were utilized for the commercial production of a wide range of fuels, solvents, chemicals and other products from biomass feedstocks. Knowledge of the effects of various independent parameters such as biomass feedstock type, composition, reaction temperature and pressure, residence time and catalyst on reaction rates, product selectivities and product yields has led to the development of advanced biomass pyrolysis processes. The accumulation of considerable experimental data on these parameters has resulted in advanced pyrolysis methods for the direct thermal conversion of biomass to liquid fuels and various chemicals in higher yields than those obtained by the traditional long residence time pyrolysis methods. So, the main product from pyrolysis, there is a I already told you in the beginning of the class that pyrolysis is a step inside the gasification, right. However, when you only go for pyrolysis reaction, our main aim is mostly to produce the bio oil or pyrolytic oil, okay, which can be further processed and can be blended as a transportation fuel, and it can have several other uses also, right. So, let us understand pyrolysis with different types of reaction conditions. So, biomass is mainly composed of long polymeric chain of cellulose, hemicellulose and pectin and some other components, volatiles, right. Now, the proportion of each end product depends on the temperature, time, residence time, heating rate and pressure, types of precursors that we are using and the reactor design and configurations. We can see how the reactions proceeds. So, less than 200 degree centigrade, what is happening, that is called as dehydration, drying or removal of the moisture, we call it dehydration. Okay. The moment you proceed beyond 200 and within the 200 to 280 degree centigrade, you can see that first hemicellulose will start degrading. So, hemicellulose decomposes. Okay. So, it will result in some amount of syngas and a minor quantity of bio oil. Then we proceed further to beyond 280 degree centigrade, and in the range of almost 300 degree centigrade, the broad range of 240 to 350 degree centigrade, the cellulose degrades. Okay. When the cellulose decomposes, it again produces some amount of syngas, some more amount of bio oil, okay, and minor amount of the biochar, that is the solid residue that will be left out. Okay. You proceed further beyond 350 degree centigrade up to 400 or 500 degree centigrade, here lignin decomposes. Okay. Lignin decomposes mostly to the biochar and certain less amount of bio oil. So, this is how the pyrolysis reaction happens. So, this is the yield of the pyrolytic products. Okay. You can see the yield of the biochar, okay, this decreases as and when we proceed with the pyrolysis reaction, okay, or we increase the temperature. So, this is the yield of bio oil. You can see that the most amount of the highest yield is about this 500 degree centigrade. You beyond that it decreases, because beyond that lignin is decomposed. Lignin is not resulting more into bio oil, it is more it is getting converted more into your biochar. Okay. Then there is gas and water also. So, a modern technology was developed to extract maximum possible energy from biomass using combustion, which is a exothermic reaction, gasification, which is another exothermic reaction, and then pyrolysis, which is an endothermic reaction. Pyrolysis can be considered as part of gasification and combustion. This is what I already mentioned you. So, these are some of the end products and the temperature and the type of reactions. So, less than 350, moisture loss, depolymerization, we get carbonyl and carboxyl group production. This is what I have already described, but this is given in a tabular format for a better understanding. So, between 350 to 450, you get breaking of glycoside chain of polysaccharides. So, tar production begins that contains levoglucosan, anhydrates and oligosaccharides. Above 450, dehydration, rearrangement and fission of sugar units happens. You get acetaldehyde, glycoxylene, acrolein production and some other components. Above 500 degree centigrade, a mixture of all the processes, reactions that is happening, and mixture of all the above products also being produced. So, then condensation reaction happens. So, unsaturated products condense and cleave to the char. A highly reactive char residue containing trapped free radicals is the end product. So, conventional pyrolysis consists of the slow irreversible thermal degradation of the organic components in biomass, most of which are lignocellulosic polymers in the absence of oxygen. So, pyrolysis is happening without oxygen, okay, whereas gasification is happening, which happens after the pyrolysis with a less amount of theoretical oxygen that is required for the, which is required for the combustion process. So, slow pyrolysis has traditionally been used for the production of charcoal. Short residence time pyrolysis, which are flash pyrolysis, ultra pyrolysis of biomass at moderate temperatures can afford up to 7 to 8% yields of the liquid production. So, they are very good in producing higher amount of bio oil. Pyrolysis conditions can be used that provide high yields of gas or liquid products and char yields of less than 5%. One configuration of an advanced biomass pyrolysis system, for example, involves an ablative vortex reactor for pyrolysis at biomass residence times of fractions of a second coupled to a downstream vapor cracker. Overall, the pyrolysis process can be classified as slow and fast depending upon the heating rate. In slow pyrolysis process, the time of heating the biomass substrate to pyrolysis temperature is longer than the time of retention of the substrate at characteristic pyrolysis reaction temperature. However, in fast pyrolysis, the initial heating time of the precursor is smaller than the final retention time at pyrolysis peak temperature. Based on medium pyrolysis can be another two types, namely hydrous pyrolysis and hydropyrolysis. What medium is being used? So, a slow and fast pyrolysis is usually carried out in inert atmosphere, whereas hydrous pyrolysis is carried out in the presence of water and hydropyrolysis occurred in the presence of hydrogen. So, this table gives you the types of pyrolysis process with resultant products. So, fast pyrolysis, the retention time is extremely slow, okay, once to less than 2 seconds. Rate of heating is very high, final temperature is around 500 degree centigrade and the major product that you get is the bio oil. The highest yield is of course bio oil. Flash pyrolysis less than 1 second, okay, extremely fast. High rate of heating less than around 650 degree centigrade and again the major product is bio oil and certain chemicals and maybe gas, less amount of gas. Ultra rapid less than 0.5 second, very high rate of heating, the temperature is required is 1000 degree centigrade, you get chemicals and gases. Vacuum pyrolysis you get bio oil, okay. Hydropyrolysis less than 10 second, high rate of heating, temperature required is less than 500 and the major product is bio oil. And carbonization this is the slow pyrolysis, okay, which was initially used so many years before to produce the charcoal. So, the resultant product is charcoal and less than 400 degree centigrade. Conventional is about 5 to 30 minutes, low many times we can call it as a intermediate pyrolysis. So, the temperature maximum temperature we can go depending upon the type of feedstock is 600, you get so many different types of products and a certain proportion char, bio oil and gas. However, again depending upon the type of feedstock maximum yield is of course of the bio oil. So, fast pyrolysis. So, during the fast pyrolysis process biomass residues are heated in absence of oxygen at high temperature using higher heating rate. Based on the initial weight of the biomass, fast pyrolysis can provide 60 to 75% of the liquid biofuels with 15 to 25% of the biochar residues. So, the process is characterized by small vapor retention time. However, quick chilling of vapors and aerosol can ensure higher bio yield. So, this is another further step. So, you get a pyrolysis oil here, non condensable gases you can be burnt can be processed through the gas burner and you get the heat, again that heat can be used in the pyrolysis here. So, the pyrolysis oil you can see that so many different types of processing here, synthesis and extraction to bio based chemicals. It has I can tell you again we have already discussed once the product, the major product from the fast pyrolysis or any pyrolysis of course is the oil, okay, that is the major aim. Whenever we generate oil, so you just leave it or settle it under gravity, allow it for some time, okay, you see that two distinct phases, okay, one top phase and bottom phase, there is phase separation. So, one phase is containing the oil rich phase, okay, that is the organic components and that is if we decant it properly and take it out and further process, that is the bio oil. And there are other portion which is aquatic phase, okay, that aquatic phase contains so many different types of chemicals and some of these chemicals can be of very high value depending upon what is the feedstock you are using, that can be processed, you get that type of platform chemicals here. Upgrade you get advanced biofuels, if you can go for some sort of distillation process. Feed to turbine engine, you get a clean power here, boiler you get heat, and whatever the biochar that leaves, it can either be burnt in a boiler to produce the heat, maybe steam at certain cases, or it can if the quality of the char is poor, it can be used as a soil enhancer. Fast pyrolysis technology is getting implausible acceptance for producing liquid fuels due to certain technical advantages. So, some of them are listed here. So, it can ensure preliminary disintegration of the simple oligomere and lignin process from the lignocellulosic biomass with successive upgrading. The scaling up of this process is economically feasible. It can utilize second generation bioil feedstock such as forest residues, municipal and industrial waste. It provides easy storability and transportability of liquid fuels. It can ensure secondary transformation of motor fuels, additives or special chemicals. Then is flash pyrolysis. So, this is a flash pyrolyzer or flash pyrolytic reactor. So, flash pyrolysis process of biomass can give solid, liquid and gaseous products. The bioil production can go up to 75% if you use this particular technology. This procedure is carried out by speedy devolatilization under inert atmosphere using higher heating rate with high pyrolysis temperature around 450 to 1000 degree centigrade. So, in this process the gas residence times is less than 1 second, is too little. Okay. So, nevertheless, the process has poor thermal stability. Due to catalytic effect of the char, the oil becomes viscous and sometimes it contains some solid residues also, which is not desirable, but you can further process it to take out the solid part. Then slow pyrolysis. Slow pyrolysis can yield good quality charcoal using low temperature as well as low heating rates. The vapor residence time can be around 5 to 30 minutes in this process. The volatile organic fractions present in vapor phase continue to react with each other to yield char and some liquid fractions. The quality of bioil produced in this process is very low. So, if your aim is to produce bioil, it is recommended not to use slow pyrolysis. You can better to go for an intermediate pyrolysis where you get a good amount of bioil, and if you only want oil, then you can higher bioil yield, then you can go for the fast pyrolysis or flash pyrolysis. Okay. So, the longer residence time in slow pyrolysis initiates further cracking to reduce the yield of bioil. The process suffers from low heat transfer values with longer retention time, leading to enhance the expenditure by higher input of energy. The stoichiometric equation for production of charcoal is shown by this equation. C6H10O5 gives rise to 3.74 carbon plus 2.65 water plus 1.17 carbon dioxide and 1.08 methane. Then let us understand catalytic pyrolysis. A mixture of hydrocarbon was produced earlier from methanol over zeolite stack ZSM5. Another patent suggested that passing the vapors from pyrolyzer over a bed of zeolite ZSM5 to produce short chain hydrocarbons. It was reported that the catalyst of ZSM5 can convert bioils generated from the pyrolyzer to alkylated benzene. The disadvantage of using ZSM5 as catalyst was coke formation. Now, however, these disadvantages can be overcome by using a circulating fluidized bed technology, where the fluidized bed can be prepared using different types of catalysts instead of sand. So, this CFB we have whatever discussed under the gasification, the same reactor can be used. Catalyst can be mixed with lignocellulosic substrate earlier to pyrolysis process or separately with the gaseous reactants to obtain desired products. So, this statement you will see many times it will be you come across with two different terminology. One is called ex situ pyrolysis, catalytic pyrolysis, one is called in situ catalytic pyrolysis, where the in situ catalytic pyrolysis the catalysts are physically mixed with the biomass, then we go for the pyrolysis reaction. In ex situ pyrolysis reaction, what happens that there is a fixed bed type of reactor, it can be fluidized bed also, okay, where the biomass is not mixed with the catalyst. So, the catalyst is kept in a separate section, and when the vapor is getting generated from the after the pyrolysis reaction from the feed biomass, okay, that passes through a bed of catalyst. So, the catalytic cracking is happening for the vapor phase. So, you can call it vapor phase catalytic cracking. Okay. That is better because this catalyst can be regenerated and reused, whereas if you mix with the feedstock, then you cannot take away or you cannot separate the catalyst from the biomass, and it will be waste basically. And you know the catalysts are extremely costly, most of the catalysts, commercial catalysts. So, it was revealed that parting of the catalyst and biomass was more operative for the transformation of the required products. So, catalytic hydropyrolysis. So, catalytic hydropyrolysis is a kind of catalytic pyrolysis, where pyrolysis is carried out using fluidized bed reactor under the flow of hydrogen. In this process, the fluidized bed is replaced by a transition metal catalyst. It was reported that the replacement inert sand with nickel based catalyst under atmospheric pressure can convert the bio-oil into low molecular weight hydrocarbons within short contact time. Recently, Gas Technology Institute in Illinois, United States reported a new process where the overall process is carried out under 7 to 34 bar pressure. Due to high pressure, C1 and C3 gases are evolved, which after reforming produce large amount of hydrogen. However, the system is also very complex, as it is a combination of hydropyrolysis and reforming. Overall, the establishment of this process is very costly. So, we will see certain types of reactors. The first is the fixed bed reactor. Okay. So, this is a very simple technology that gives priority to the production of bio-oils, okay, which are relatively uniform in size with low fines content. So, it is made up of two basic components, that is the gas cooling compartment and the cleaning system by filtering through the cyclone, wet scrubbers and dry filters. So, here this is a gas distributor which is distributing the sweeping gas. Okay. Here you feed your biomass through a feeder, okay, and it is a fixed bed. Pyrolysis reaction happens, the heat is being supplied, and whatever the resultant is the vapor, gas and aerosol. Okay. So, during reaction the solid sample is allowed to pass through a vertical shaft, where it encounters an upwardly moving counter current gas stream product. This reactor can be made using either steel, fire bricks or concrete, and composed of the feeding unit, a unit for removing the ash and the gas escape unit. The reactor, which has its priority for applications involving small scale heat and power, has high ability to conserve carbon and can operate for long time for solid residence, low gas velocity and of course, with a low ash carryover. It has its own limitation in the problem is usually encountered during the tar removal. Then fluidized bed system, the unit looks like similar, it is a schematic. Here it can be little something conical like shape, maybe depending the different designs available, but the bed is fluidized, it is not a fixed bed. Okay. The remaining things are same. So, this reactor consists of a mixture of two phases, the solid and the liquid, and usually accomplished by passing a pressurized fluid through the solid material. Now, there are different types of fluidized bed reactors, which include bubbling fluidized, circulating fluidized, ablative reactor, vortex reactor, rotating dish reactor, vacuum pyrolysis reactor and rotating cone reactor. There are many different designs are available, and this is the simplest schematic. Okay. So, the advantages of fluidized bed are the provision of heat transfer is very rapid. Okay. It has a good grip of pyrolysis reaction and vapor holding time control. It has sufficiently high surface area for contact between the two phases in the mixture, because they are suspended, the biomass is in suspended medium. The heat transfer in the system is exemplary and the relative velocity between the phases is very high. So, then the next is bubbling fluidized bed reactor. So, the high presence of solid density in the bed ensures a better temperature control, smooth contact between gas and solid, good transfer of heat and excellent storage capacity. The biomass is heated in an environment devoid of oxygen and decomposed into gas, vapor, aerosols and char, and these components are finally collected from the reactor. While the charcoal is collected using the cyclone separator and stored, the vapor is cooled rapidly and condensed into high quality bio-oil and stored with about almost 70% yield of the biomass weight and dry weight basically. Okay. Then next is the circulating fluidized bed. So, you can have a close look at the image. Okay. You can see that there are two different sections. The first one is the fluidized bed here, the main reactor here, okay, and this is the combustor. right. So, this feature of this the features of this reactor is similar to that of a bubbling fluidized bed reactor described above, except the fact that residence time for the vapors and char is shorter. This makes the gas velocity and the content of char in the bioil to be higher. However, it has a large throughputs advantage. Single and double type of these reactors are also available. Then next is vacuum pyrolysis reactor. This is a slow pyrolysis reactor with heat transfer rate very low. This results in a lower bio yield, usually in the range of 35 to 58%. The design is highly complicated and requirement for investment and maintenance is always high, thereby making the technology uneconomically suitable. The biomass is conveyed into the vacuum chamber with a high temperature with the aid of a conveyor meter belt with periodical stirring of the biomass by mechanical agitation. The heat carrier is usually made up of a burner, while the biomass is melted by heating inductively using molten salts. So, it has the ability to process larger particle size biomass, but requires special solid feeds, special discharging devices in order to have an effective seal all the time. Then rotating cone reactor. Unlike the fluidized bed reactor, the rotating cone reactor requires the mixing of biomass and hot sand mechanically and does not require the use of inert gas. The feed and hot sand are fed in from the bottom of the cone, while they are transported to the lip of the cone during spinning using a centrifugal force, and as they get up to the tip, the vapor generated is condensed by the condenser, and then you can collect the condensable part. The char and the sand are combusted, with the sand being heated up again and reintroduced to mix the fresh feedstock at the bottom of the cone. So, you take out the char, okay, and char, if it is getting converted and fully combusted. So, you basically end up with certain S, and having the S is having a low density, it can be easily separated, and the sand which is already containing high amount of heat can be recycled back. Though the design of this reactor might be complex, its high bio-oil yield makes it extremely desirable. So, the two different designs which we have already discussed, this is the vacuum pyrolysis reactor and that is the rotating cone reactor. Okay. So, you can have both different stages in the vacuum pyrolysis reactor. You can have a single stage also, you can have multiple stages also. Then whatever it is coming out, okay, biomass is usually fed from the top, or if it has different distinct stages, so you can feed from this side also. You get there is a condenser which condenses the liquid, and you get the liquid here, and the char can be collected from the bottom. Again, in the rotating cone reactor also, biomass as well as the hot sand which is carrying the heat is being fed from the top, and the cone is rotating. Okay. So, we will just summarize. So, advantages and disadvantages of different pyrolysis reactor. If you look at fixed bed reactor, the advantages are simplicity in design, reliable results, and biomass size is independent. Okay. No fixed biomass size is required. However, the disadvantages are high carbon conservation, long solid residence time, low S carryover, and difficult to remove the char. If you talk about bubbling fluidized bed, the advantages are the design is simple and easy operational procedures. However, it suffers from good temperature control, and this one suitable for large scale application. Small particle sizes are needed. There is a small mistake here, actually the good temperature control will come to the advantages. Okay. And for the circulating fluidized bed, the advantages are well understood technology, better thermal control, large particle sizes can be processed. Disadvantage is that large scale production difficulty, complex hydrodynamics, and char is very fine. So, that char cannot be utilized for any better purposes, you can restrict itself to only soil amendment. Okay. Rotating cone, advantages are centrifugal force circulates hot sand and biomass substrate, no carrier gas is required. Difficulty is that operational processes are a little having disadvantages position, smaller particle sizes needed, otherwise you cannot circulate them. Okay, they will deposit on the bottom. Large scale application is difficult. If you talk about vacuum pyrolysis, the advantages is that the oil that you get out is from this particular reactor is very clean. Can process larger particles of 3 to 5 centimeter, no carrier gas required, lower temperature required, condensation of liquid product is very easier. The disadvantages is that it is a slow process, solid residence time is too high, requires large scale equipment, poor heat and mass transfer rate, and it generates more water. So, we will talk about the pyrolysis mechanism. So, many dehydration, cracking, isomerization, dehydrogenation, aromatization, coking and condensation reactions and rearrangements happen during the pyrolysis reaction. So, the pyrolysis reactions are very complex and predicting them for a particular biomass is too difficult. The products are water, carbon oxides, other gases, charcoal, organic compounds, tar and polymer. When cellulose is slowly heated at about 250 to 270 degree centigrade, a large quantity of gas is produced consisting chiefly of carbon dioxide and carbon monoxide. Initially, small amounts of hydrogen and hydrocarbon gases and large amount of carbon dioxides are emitted. The hydrocarbon in the product gas then increase with further temperature increases until hydrogen is the main product. The carbon oxide and other most other products owe their formation to the secondary and further reactions. Pyrolysis of cellulose yields the best known of the 1,6 anhydrous beta glucosane or levoglucosane as in reasonably good yields. A novel technique based on flash devolatilization of biomass and direct molecular beam mass spectrometric analysis has shown that levoglucosane is a primary product of the pyrolysis of pure cellulose. However, the yield of levoglucosane on pyrolysis of most biomass is low, even though the cellulose content is about 58%. Although also when pure cellulose is treated with only small amount of alkali, levoglucosane formation is inhibited and a different products slate composed of furan derivatives are produced. So, this is the reaction you can see of the beta glucosane formation during pyrolysis. This is from the beta D glucose, it is a mixture. Here it can be from cellulose or starch. So, levoglucosane is also obtained directly on pyrolysis of glucose and starch. The compound has the same empirical formula as the monomeric building block of the cellulosic polymers. So, with this I wind up and thank you very much. So, in the next class we will be discussing about the thermal conversion products, what are the different types of products, their composition, their applications and some certain commercial success stories about the gasification and pyrolysis. Thank you very much. If you have any query, please feel free to register it in the SWAYAM portal or drop a mail to me at kmohanty@iitg.ac.in. Thank you.